Okay, so chapter 10 is all about solutions. Okay. So before we can know more about the solutions, we need to actually define what the solution is. Okay. So a solution is defined as a, let me look in these regions. Homogeneous mixture of two or more substances in one single phase. Okay. So when we say the homogeneous mixtures, okay, what does this mean? Okay, these need to be homogeneous at the either the molecular or atomic level. Okay, so this is the key. Okay, so a few things before we can actually elaborate this a little bit more. Let me actually just introduce the important components that we need to know. Okay, a solution has two components. Okay, one is called solute. Okay, the other one is called solvent. Okay, so the solute is the less abundant species inside the solutions, and the solvent is the more abundant species inside the solution. Okay, when you have solute plus your solvent and form a homogeneous mixtures, you got your solution. Okay, and then we always say the solute is dissolved in the solvent. Okay, so that's how we define the solutions. Okay, so the very simple definition, okay, basically is you have your solute, you have your solvent, you blend together, they form a homogeneous mixtures at the molecular or atomic level. We call it as a solution. Okay, so example of solutions. Okay, hope this will give you a better idea. Okay, salt water is actually a solution. Okay, inside here we know the solvent will be your water or H2O. Okay, and the solute will simply be just your salt. Okay, to give you more chemistry flavors, it will be just sodium chloride. Okay, so one thing you want to be careful is actually if you throw in your sodium chloride, which is actually the white solid, if you put it into the waters, the white solid disappear, right? Because the sodium chlorides, when they dissolve inside water, they become sodium plus and chloride minus, and those things actually surrounded by the water molecules. Okay, then they form a homogeneous solutions. Okay, so we call this is actually a liquid phase solution. Okay, another thing is actually the sugar water. Okay, sugar water. Okay, sugar have this very unique chemical formula. Okay, it also look like a white solid powders when you throw it in. You also dissolve inside the solvent, which is your water. And then after a while, it becomes also transparent. Okay. So once they dissolve inside water, okay, this one did not do the things like sodium chloride. It just exists as the sugar form. Okay, but it forms hydrogen bonds with your water so that you actually stay let molecular forms inside water. Okay, so it also form a very stable solutions. Okay, but solutions doesn't necessarily to be in the liquid phase. It can also be in the gas phase or the solid phase. Okay, air is actually one of the most commonly seen solutions. Okay, in the gas phase. Okay, so if you consider O2, which inside our air, we have around 20% of O2. Okay, so O2 is our solute. There you go. 80%. Okay, so inside our air, 80% are nitrogens. Okay. So these are the actually example of the solid solutions. Okay, so brass is actually one of the metals that you see a lot. Okay, so the majority of brass is actually coming from copper. That's why you see these shiny gold colors on the brass. Okay, but inside there, there's actually a certain percentage is actually coming from the zinc. Okay, and they form a homogeneous solution. Okay. Okay, so another things maybe most of the females will be interested in is actually the ruby. Ruby is also a solution. Okay, so majority is actually just aluminum oxide. Okay, but with certain solutes make it become a very valuable jewelry. Okay, I guess that's something that you want to know in the future. Okay, once you get a ruby from your significant halves. Okay. All right, so let's actually some examples of solutions in either liquid, gas, or solid phase. Okay, so what are the species that doesn't consider as solutions? Okay, so these are the two examples. Okay, so the mud waters is not a solution. Okay, so one thing for the liquid solutions, okay, one thing people consider a solution, okay, in the old time, okay, the way people judge it is actually through the how transparent the solution is to consider is actually a solution or not, okay. But as time goes by, okay, right now in the past couple decades, okay, we human actually inventing a lot of things, including this uh, nanoparticle uh, solutions or mixtures, okay? So it also looks transparent, so that definition become less useful, okay? So like the mud waters, okay? So when you have the mud waters, it actually looks very cloudy, okay? So what happened inside is actually your water is still water, okay? Your mud is actually a tiny dust inside your solution, okay? So these little dots represent the sand or the little solid materials, okay, they did not actually interact with your water at all, okay. Therefore, they just suspend inside the solution, okay. Under these situations, we call it heterogeneous solution, okay. So most of the things we talk about in this class was defined as this homogeneous mixture, okay, not a heterogeneous solution, okay. So if today I ask you, okay, is sodium chloride water mixture, is this is a solution or a not solution? Okay, the answer will be okay. The sodium chloride aqueous mixture, it is a solution. Okay. So for chapter 10, okay, all the things that we talk about will be actually fall within this aqueous solution, which means is actually the solvent is always the water. Okay. So depending on the type of solute you have, okay, you can either have the electrolyte solution. That means the species when it goes into your water solutions, it dissociate so that you have the both anions and cations coexist inside your water solution. Okay. For the non-electrolyte solutions, all you have is actually just the molecule itself. Okay. For example, the sugar. Okay. Once they dissolve inside your water solvent, okay, they actually stay the same form as sugar. Okay. So structure-wise, it did not produce any cations or anions coexisting inside the water. Okay. So electrolyte solution and non-electrolyte solution, the the way you make the judgment is whether you have these positive or negative charges coexist inside the solution. Okay. The next natural question people will ask is actually how concentrate the solution is. Okay, so basically for the dilute solutions, okay, you have fewer solute molecules compared to the more concentrated solution where you have tons of solute molecules existing inside your solvent. So what we are going to do today is actually we want to introduce you the concept about 5 different definitions of concentrations. Okay, and I will give you the definitions. I will give you one examples so that you know how to do all these calculations. So the first concentration we are going to talk about is called the molarity, which you already know for a long time. Okay, so the definition of molarity will be okay. So your numerator is actually number of moles of your solute divided by the volume of your solution. Okay, and the solution must have the unit, the volume must have the unit of liters. Okay, on the top is actually have a unit of moles. Okay, and then you should already know this very well by now. Okay, the number of mole of your solute can be calculated through the mass of your solute divided by the molecular weight of your solute. Okay, so give you one examples. Find the molarity if 5.22 gram of sodium chloride is dissolved in enough water to form 125 solution. Okay, so when you read these type of questions, first you need to know what you have, right? 5.22 gram of sodium chloride. Okay, so you need to know what this is, right? So from here, you should know that the mass of your solute is going to equals to 5.22 gram. Okay, and then the things you want to calculate is actually your molarity, right? That means you need to know number of mole of your solute, and then you also need to know the volume of your solution in liters. Okay, so when you read this one, you know eventually you have 125 ml of solutions, right? So that means actually your V solution is actually 125 ml or 0.125 liters. Okay, and to calculate your number of mole of your solute, then you need to know the molecular weight, right? And then we know the molecular weight of your sodium chloride is going to equals to 58.44 at the unit gram per mole. Okay, so what you do is actually 5.22 divided by 58.44. Okay, so that will give you the number of mole of your solute. From these two, then you can calculate your molarity is equals to number of mole of your solute divided by the volume of your solution. And this will give you a number of 0.715 m. Okay, so let's how you solve these molarity problems. Okay, so basically when you see the molarity, the first thing you do is actually to know the definition of this. Okay, and then you read this one and you know what is missing here. Okay, so from the reading you know you can get this quickly. Then you need to know how to calculate your number of mole of solutes. Okay, so when you calculate this one, then you need to know the mass of your solute. You also need to know the molecular weight of your solute. Having these two information allow you to calculate the number of mole of your solute And with these two, you can calculate your molarity. Okay. So it's actually very straightforward. Okay. Another things that you will know is actually how to calculate this so-called normality. The calculation is actually very simple. Okay, it's just your molarity multiply the number of equivalent. Okay, let me zoom in this one a little bit so I have more space to write. Okay, so what is number of equivalents? Okay, so this is actually typically relevant to these two type of solution. One is so-called the acid-base solution. The other one is oxidation reduction solution. Okay, so I assume everybody know what acid is, right? So the acid is actually a species. Okay, once it dissolves inside the water, it will produce the protons. Okay, here I use the hydrogen chloride as example. Okay. So in this case, you can see for this acid solution, one hydrogen chloride produce one protons, okay, in the equation. Okay. But sometimes we have this acid, for example, the sulfuric acid, okay, once they dissolve in water, it actually produce 2H plus SO4, 2 minus, okay, on the top should be Cl minus, okay. So you can see one acid solute produce two hydrogen protons here, okay. So under this case, we can define the number of equivalent is going to equals to 2 because one sulfuric acid produces two equivalent protons. Okay. So using this concept, then you can actually solve this one very easily. Okay. So because we know the normality is just the concentration, okay, of molarity, okay, which is 3.75 times the number of equivalent. In this case, you know your H2SO4, the number of equivalent is equals to 2, right? So simply multiply by 2. Then you know the answer will be 7.50 N. Okay? So let's how you calculate the normality. Okay? So what makes this one more difficult is actually you need to have the concept, okay, to see, okay, if you have a solute species, okay, do you know how to obtain the number of equivalents? That's actually the more challenging part, but that's actually based on your chemistry knowledges, okay? But it's not as difficult as you saw because the most commonly case is actually the acid base, okay? So by looking at the chemical structure or chemical formula carefully, okay, you sort of can predict, okay, what is the number of equivalents for different acid or base, okay? So another situation is actually the oxidative reactions, okay? So here actually I give you one examples, okay? For the oxidation reduction type of things, okay, at current stage, typically, if they want you to actually calculate the number of equivalent, it will actually give you the equations. So you don't have to worry too much about this oxidation reduction equation. Looks so complicated. Okay, so this is actually one example. Okay, so you can see this actually MnO4 minus. Okay, you are going to interact with 5 electrons to produce one manganese 2 plus reduction reactions. That means actually one of this is going to consume 5 electrons. So in this case, your number of equivalent is going to equals to 5. Okay. So the question here is actually asking you finding the equivalent mass of this. Okay. So first thing to know, what is the definition of the equivalent mass? Okay. So I just write here, the equivalent mass is going to equals to the mass of the target species divided by the number of equivalent. Okay. So here, you have one end of these solutions, right? So we assume there's actually 1 liter because you want to get the mass, right? So the mass always coming from the number of moles. Okay, since I have 1m, the easy way is actually just assume you have 1 liter of these solutions. That means you're going to have 1 moles of MnO4 minus. Okay, then you check out the molecular of these guys. Okay, remember we calculate the number of moles previously here, right? So the number of mole is going to equals to the mass of your solute divided by the molecule of your solute. In other words, the mass of your solute is going to equals to the mass of your solute is going to equals to the number of mole of your solute times the molecular weight of your solute. Okay. So right now you have 1 mole of KMnO4 minus. Okay. You can check out the molecular weight of that species from your periodic table. Okay. So that we can calculate the mass of your MnO4 minus is going to equals to 1 mole times the molecular weight is actually 158 gram per mole. Okay, which give you 158 grams. Okay, so you know that's how much mass you have for your MnO4 minus. Okay, then you know the equivalent mass will simply equals to the molecular weight of your MnO4 minus divided by the number of equivalent. So that will equals to 158 divided by 5. Okay. So that will give you the equivalent mass equals to 31.6 gram. Right, the next one is actually the mass percent. Okay, so the mass percent is actually defined as the mass of your solute divided by the mass of your solution. Okay. Okay, so the mass of your solution can also be rewritten as the mass of your solute plus the mass of your solvent. Okay, so it's very straightforward, just using the mass instead of using number of moles. Okay, so another one is actually mole fractions. Okay, so mole fraction means actually need to use everything using number of moles. Okay, so again, it's number of moles of your solute divided by number of mole of your solution is equals to number of mole of your solute plus the number of mole of your solvent. Okay. So if you look at these questions, find the mole fraction of KBr if that much KBr is mixed with that much water. Okay, so here you need to know which one is solute, which one is your solvent. Okay, apparently KBr is actually your solute. All right. So for the number of for the mole fractions, okay. So for this question, then we need to calculate the number of mole of your KBr. Okay, again, it's actually the mass of the KBr divided by the molecular weight. Okay, so here the mass of your KBr is 7.31 gram. Okay, and then the molecular weight, if you check out your periodic table, is actually 119. Okay, and this gives you a number of mole equals to 0.06143. Okay, then you need to know the number of mole of your solvent. Okay, solvent is actually your water, right? So just H2O. Okay, so the mass of your water over the molecular weight of your water, and that's equals to 50.0 divided by 18. So they will give you a number of 2.775. Okay. Then you can calculate the mole fractions of your KBr is going to equals to the number of mole your solute is 0.06143. Okay, and then divided by the sum of these two. So that's 0.06143. Plus 2.775. Okay, so you are going to get a number of 0.0217. Okay, so if you want to calculate the mole fractions of H2O, okay, what you do is actually you need to put the number of mole of H2O in the numerator, okay, and the button is actually, again, the same is actually 0.06143 plus 2.775. Okay, so these are the four concentration quantification methods. Okay, so overall you can see on the top is always number of mole of your solute or mass of your solute. At the bottom is always either either the volume of the solutions or the mass of the solutions or the number of mole of the solution. Overall, I think for this part, okay, for this page, these four different concentration terms, the concept is always solute over solution, okay? So that's the concept for this four, okay? And then the very last concentration that I intentionally actually put on different pages is actually this, the molality. Okay, because for molality, it was defined as number of mole of your solute divided by the mass of your solvent. Okay, so this is actually very different from the other four. This is actually the only one that your denominator is actually divided by a property of your solvent only. Okay, not solution anymore, it's actually solvent only. Okay, and this is actually the mass of your solvent with a unit of kilogram. Okay, so this is actually the only concentration terms that has the solvent, okay, in the denominator. So it's very important because so many students get so confused about when I should use solvent, when I should use solution. And the easiest way to remember this is actually the molality is actually the only concentration terms that use solvent at the denominator. Okay, so I think having this separate from having the molality separate from the other four will help you to actually memorize this. Okay, so this morning I say I update the PDF. This actual part I update because I feel like if I present this way, it's easier for you to memorize that the molality is actually the only one that in the denominator calculation is actually using solvent, not the solution. Okay, so here shows the example. Okay, so find the molality of 10.5 kBr is dissolving in 212 of water. Okay, so based on the definition that you know, you want to know the number of mole of your solute. Okay, which you know you need to calculate the mass of your solute divided by the molecular weight of your solute. Okay, so then you can know you need to put 10.5 divided by kBr, the molecular weight is 109. Okay, and then you know the mass of your solvent. Okay, it's very important. It's solvent, not your solution. Okay, is 212 gram, which equals to 0.212 kilogram. Okay, so once you have this, then you can calculate your molarity. It's going to equals to number of solute is this guy divided by this guy. So I think I should make this one more clearly. Okay, so 10.5 is gram, right? When you calculate your molecular weight, okay, if you check out all those things, also numbers on your periodic table, when you're adding up, you actually have the unit of gram per mole. Okay, because your molecular weight has a unit of gram per mole, this will cancels out. Okay, so let your number of mole. Okay, so this will give you a unit of mole. Okay, so that's why I did not need to convert this one into kilogram, because when I convert it into number of moles, the molecule will have the unit of gram per mole. So the calculation here will be actually just this divided by that. Okay, then you got the answer of 0.416 m. All right, so that's all the concentration terms that you need to know. Okay, so let's have a quick summary. Okay, so the first summary is actually we know the solutions. Okay, it's from a very simple idea. The solution is going to be composed of your solute and your solvent. Okay, and we also know the mass of your solution is going to equals to the mass of your solute plus the mass of your solvent. Okay, so this is always true. Okay, so the mass of your solution is equal to mass of solute plus mass of solvent. It's always true. Okay, so and then we also know the number of moles of either your solute, solvent, or solute. Actually, your solute and solvent. Okay, it can always be calculated as by the mass of your solute or solvent divided by the molecular weight of your solute or solvent, where you get molecular weight is actually obtained from your periodic table. Okay, and this is actually typically given in the questions. Okay, so those are the things that you need to know. Okay, then let's go back to the 5 different concentration that you have learned so far. Okay, So first one is actually the molarity, right? The capital M. Okay, so what it needs is actually you need to know the volume of your solution, okay, and the number of mole of your solute, right? So your M is simply equals to number of mole of your solute divided the volume of your solution, okay? And then we know the normality, okay, is just equals to the molarity times the number of equivalents, okay? Then we learn about the mass percent, okay? So for the mass percent is we need to know the mass of your solution, okay? And then the mass of your solute. Okay, when you calculate, it will be just the mass of your solute divided by the mass of your solution times 100%. The only things that can be changed when you look at the one questions is actually the mass of solutions. Okay, is often in combined with this. Okay, it may not actually give you the mass of solution directly, but it gives you the mass of your solute and mass of a solvent. Then what you need to do is actually to calculate the mass of solution from this equation. Okay, then all the calculation will be actually very straightforward. Okay, then the next one is actually the mole fractions. Okay, in order to get the mole fraction, you need to know the number of mole of your solution and then the number of mole of your solute. Okay, so you know the mole fractions is just equals to the number of mole of your solute divided by the number of mole of your solution. Okay, so you can see all this four is actually the denominator is actually your solution. Okay, the things that's different is actually your molality, right? Because the molality actually is going to require the number of mole of your solute, okay, and the mass and the mass of your solvent. Okay, so the molality is equals to number of mole of your solute divided by the mass divided by the mass of your solvent. And here is actually in kilogram. Okay, so this table pretty much summarizes all the calculations. Okay, there's actually one more thing that you need to know because one of the very big things that you are going to encounter many times in your homework is actually conversion between different concentration. Okay, so the things that were, so there's actually one more thing you need to actually know to convert between uh, the different concentration terms. Okay, so that conversion actually requires the another equation is called the D is equals to mass over V. Okay, so density of the solution is equals to, let me rewrite this again so you don't get confused. So the density of your solution is equals to the mass of your solution divided by the volume of the solution. Okay, so if in the questions you see it provided density, okay, that means you need to actually calculate it will give you actually 2 out of these 3 terms. Then you can calculate the third one. But most of the time, it gives you the density, it gives you the mass of your solutions. So in this way, it actually tell you what's the volume of the solution. Okay, and that typically is going to ask you to convert to the molarity. Okay, so this is actually a quick sum up about the things that is going to, the information you need to use to convert between different uh, concentration terms. So here is actually the first example, okay? Converting the molarity to molality. Okay, you have 3M HCl. Okay, the density of this solution is that much at that degrees. Okay, so 3N, you know, that's actually the molality, right? So for all these conversion questions, okay, depending on where you get started, okay, you make that expressions, you need to actually make different assumptions, okay? But the bottom line is actually make the denominator equal to 1. They will make your life a lot easier, okay? So for example, here you start from 3M HCl solution, okay? So you know 3M means what? Means this is actually molarity, right? So it's actually number of moles of your solute divided by the volume of your solution. Okay, so assume our denominator is equals to 1, which means actually I assume my V solution equals to 1 liter. Then I know the number of solutes is going to equals to 3 moles. So from here, you can easily see that, okay, it's very easy to actually obtain the number of mole of solute if you make the proper assumption, okay? Then you want to convert the molarity to molality, right? So we know the molality is going to equals to the number of mole of your solute divided by the mass of your solvent. Okay, so this turn, you already know the answer, right? So how do you get the mass of your solvent? Okay, so you can see that, okay, it provides you the information of density, right? So let's say density of your solution is equal to 1.05. So the density of the solution is equals to the mass of your solution divided by the volume of your solution. Okay. So here you know from the question, you know your density is actually 1.050 gram per mil. That's your density. You don't know the mass of your solution, but you do know the volume of your solution, right? Because we assume it's actually 1 liter. 1 liter is actually 1,000 mil. Okay, so that you know the mass of your solution is going to equals to 1,050 gram. Okay, but that's not what you are looking for, right? You're actually looking for the mass of your solvent. Okay, so you need to know. You also need to know the mass of your solution equals to the mass of your solute plus the mass of your solvent, right? So mass of your solute, since you have 3 moles of solute, then the mass of solute is actually number of mole of your solute times the molecular weight, okay? And then that is going to equals to 109.38 gram, okay? Plus the mass of your solvent. Okay, and then your solution is actually 1050. So from these equations, you can actually calculate the mass of your solvent. Okay, once you get that, you plug it back in here. then you can actually get your mass. You can get the molarity of your solvent, okay, which the answer will be 3.189 m. Okay, so that's actually the typical calculation you're going to encounter for this change of expression of concentrations. Okay, so I don't think I have time to actually go through this and this. Okay, but I will upload my Hangout to tell you how to actually finish all the calculations from here all the way to here. Okay, but the idea is actually all very simple. Okay, the rules you use is really summarized right here. Okay, on this table. Okay, so the first one is actually the mass is always conserved. The mass of your solution is equal to the mass of solute plus mass of your solvent. Okay, the number of mole is always calculated from the mass of the species divided by the molecular weight of that species. Okay, where the molecular weight is actually obtained from your periodic table. Okay, and then here we also mentioned, okay, for this 4 concentration terms is always number of solute divided by the property of your solution, either the volume, the mass, or the number of mole of your solutions. Okay, so it's all summarized here. The molality is actually the only exceptions because even though the numerator is actually still the number of solute, but the denominator is actually mass of your solvent, not solution anymore. So this is actually the part that students actually got confused so much. Okay, and then in order to actually do the conversion between different concentration expression terms, this is actually another thing that you need to know. Okay, in other words, this table actually summarizes all the equations to memorize to do a proper concentration conversion between different expression terms. Okay, so I guess I will stop here, and then for you, okay, please work on this. Okay, I will upload how you can actually go from here all the way to this, okay, with a new Hangouts, okay, which I will upload very soon. Okay, but before I upload it, okay, try to do these things yourself using the knowledge you gain in this lecture.